Hello and welcome back to our fifth hands-on in our artificial intelligence course. In this hands-on, we will now use logistic regression and the scikit-learn packages to do predictions on our genotype dataset from before. So before we start with the programming part, please go to Moodle and download the plant flowering time binary.csv file and the plant genotype file. The plant genotype file you might know from our lectures before, which contains a lot of different plant individuals, and for each of the individuals we measured 149 features, which are 149 mutations for each of the accessions or the samples. And the plant flowering time binary file contains for each of the samples a label 0 if they are early flowering and label 1 if they are late flowering. So what we would like to predict now in this example, if we can, based on the genotype, predict if a plant flowers early or if a plant flowers late. So we will use logistic regression for this. And before we do the logistic regression, we will first import the data in all the libraries we might need. So as usual, we import matplotlib inline, and we import pylab spl, import numpy smp, we import from sklearn, we import datasets, and from sklearn model selection, we import grain test split. Then we load the data from the CSV file, therefore we use numpy, so our data matrix x is equals to np.loadtxt plant genotype.csv, and as delimiter we use the comma, so we split the columns by a comma, and our phenotype y, our target variable y, is np.loadtxt plant flowering time binary.csv. And the first thing what we should always do is we split the data into a training and into a testing set. So we write now x, x test. So we will remove some data from x for the testing, and then we override x again with the training set. So, and then y, y test, and then we do the train test split of our data. So we pass here our data matrix x, our target variables y. We say the test size should be 0.2 and the random state should be 20, that we are all on the same page. So now we split the data here and we remove 20% and put this 20% into a testing set, and then we override the original data sets x and y with the training set here. Then we do an additional split. We do an additional split to split x and y into training and validation. So x train, x validation, y train, y validation is equals to train test split. And now we pass x and y again. Please note x and y are now smaller than here because we already reduced the size here. Then we say the validation size should be 0.2. So 20% should go into the validation data set, and we set another random state which is also equal to 20. So let's execute this, and then we can say x.shape. So x has shape 557 samples and 149 features, and x train shape is 445 samples in the training set, and we have x val.shape in the validation data. We have 112 samples and x.test.shape has 140 samples are left for testing. So now we can use or train a simple linear regression model. So first let's look at the scikit-learn documentation. In the package linear model of scikit-learn, we have the model logistic regression. And logistic regression takes a lot of parameters. So here you can see it has a parameter penalty. If we go here, then we see that we can choose different penalties. We can choose the L1 penalty, L2, or elastic net, or none. So all the penalties we have looked at in the lecture, you can select here as well. When you like to do a simple logistic regression without any penalty term, without any regularization, then we have to set here the penalty to none. That's the first thing what we would like to do, and this do here. So I write this down here. So we first import from sklearn linear model, we import logistic regression, and we import from sklearn metrics, the metrics package that we can compute precision and recall and so on. So let's first train the model. So our model is logistic regression, and our penalty in logistic regression should be set to none. And then we say, okay, we train the model, model.fit, and for training the model we pass the training data, so xtrain and ytrain. Then let's test how the model performs. So predictions on validation data. So ypred is equals to model.predict x val. So first we train the model on the training data, and now we test the performance of the trained model using the validation data. And then we can compute different metrics that are important for evaluating the classifier. So we can compute the accuracy is equals to metrics.accuracy score. Accuracy score. And there we have to pass the true values, so yval, and the predictions, ypred. And then we of course can compute a series of other metrics which are usually important. That's the AUC, so the area under the ROC curve, and then we have to change this here in the ROC AUC score. Then we would like to compute the precision, which is then here the precision score. We would compute the recall, so the recall is equals to metrics.recall score of yval and ypred, and we would like to compute the Matthews correlation coefficient. So MCC is metrics.Matthews correlation of the true y values and the predictions. And then we can print the results here. So print accuracy on our validation data. Then I use tabs again to make the printout nice. So ACC, and then I copy this. Oops. And I replace this by AUC precision recall MCC. Here also change the description, so ROC AUC precision recall and Matthews correlation coefficient MCC. Now let's execute this, and then I have to change this as import scikit-learn metrics as metrics, and then it should work, but it returns another error. So now we get an error which says value error, penalty none is not supported for linear solver. So now we have to go back to the documentation. So in the documentation it says here used to specify the norm in the penalization. So the Newton CG, SAGE, or LBFGS solver support only L2 penalties. ElasticNet is only supported by the SAGE solver. If not supported by the linear solver, no regularization is applied. And here we already see what happens. So because there is no closed form solution for logistic regression, you have to use a numerical solver. And linear is the standard solver that is by default set for the logistic regression, and this does not support if we don't use a regularization. So we have to find if there is a parameter, an argument that helps us to select the solver. And here we can set the solver argument and one of the solvers to also compute the logistic regression without penalty. And there we can see, for example, that the LBFGS solver here, that it can handle L2 or no penalty. So that might be a good solver that we use to find the minimum of our model. So let's go back here. Let's go back here to our logistic regression model, and we add here solver equals to LB, let's look it up, how it is called, LBFGS. LBFGS. Now let's execute this again, and then you can see that we now get here a result. Here we have one top too much, and now we execute this, and now you see that we get the results. So we would now get the following accuracy, so 61% accuracy on the validation data, an area under the curve of 60%, a precision of 58%, a recall of 54%, and a Matthews correlation of 0.21, which indicates that the model is doing better than random, but it's not doing perfectly good. So we might be able to predict, based on the genotype, some of the accessions to be early or late flowering accessions, but it doesn't work too well. So maybe regularization helps. And before we apply regularization, it also sometimes makes sense to look at the weights, at the coefficients our logistic regression model learned. So here we said we have 149 features. So let's plot this 149 features. So let's say pl.scatter. We create a scatter plot of the beta coefficients. So np arrange x.shape 0, shape 1. So the number of features are our x, and then we plot here the model coefficients. The coefficients are the beta estimates of our model. So let's plot this, and then you see the following plot. So each individual point in this plot is now a beta value that we have estimated. And you see that they reach from minus 600 to plus 600, a little bit more and less. And some of these features get very high weight. So maybe by applying regularization, we might be able to get a better predictive model, because you also can see that some of the values here, the beta estimates, look very close. So maybe we can control for this correlatedness between the features, and by shrinking the effect of the influence of the beta values a little bit. And this we can do maybe using ridge regression. And using ridge regression, or in this case logistic regression with a L2 penalty, also helps us to get a feeling of the effect of the beta values. And that's the first thing that we like to look at. So we will now visualize the effect of alpha of the strength of our regularization on the beta, or on the model complexity. So how can we do this? So I said, when we do logistic regression with L2 penalty, we have to more or less try out different alpha values. So if we now go back to the documentation here, then you can see, okay, we can select the L2 penalty. So the rich regression penalty, but here we have logistic regression, so it's only L2 penalty. And by setting the L2 penalty, we also have to somehow set the parameter. And here we don't find the alpha, but we find a C value. And here it's a little bit different to what we have learned in the lecture, because here it says C is the inverse of the regularization strain. So this must be a positive float, like in support vector machines, which we will learn about in the next lecture. Smaller values specify stronger regularization. So scikit-learn does not use the name alpha for it. It uses the name C, and it's the inverse of the regularization strength, which means here high C values turn off the regularization, and small C values have a stronger effect on the regularization. So increase the regularization. So what we would like to do here is now we would like to try out different C values. So let's define here CS, an array of different C values, and let's say we would like to use 50 different C values between 1 to the power of -4 to 4, and we like to use 50 values. So we use the log space, we don't use a linear space where we try to find we don't use a lin space, we use a log space, and we generate 50 values between -4 and 4. And then we define an empty list train and an empty list val to store the training and validation accuracies for different C values, and then we train the logistic model for different C values. So for C and CS, we train now the logistic regression model. So LR is logistic regression. We set the C value, which is equals to C. We set the penalty to be the L2 penalty. We set a solver. Solver is LBFGS. And I also set something that's called max iter. That's the number of iterations the solver is allowed to do. So I increase it that we don't get numerical errors here. And then I fit the model. So I write LR, my model.fit on the training data. So X train and Y train. And then we do predictions. So Y prediction is equals to the logistic regression model.predict on the validation data. And then we compute the accuracy. So the accuracy is matrix.accuracy score of my true labels, my validation, and my predictions. And then I add this here to my validation list. So val.append ACC, and I copy these two lines and will do the same on the training data to see what's the difference between my validation and my training. So xtrain, and then I add this here to the training set. So let's look at the effect now, and let's plot here a graph. So what we would like to do is we would like to plot a new graph. So my figure is pl.figure of fixed size equals to 10,5. So I create a new figure. I create a subplot to get the axis, figure.add subplot. And now let's plot first the training accuracy. So for all the different C values, CS, I'd like to plot the training accuracies. So comma train, and the label is here training accuracy. The same I would like to do for all the C values in my validation accuracies. I call this the label validation accuracy. And then I add some axis information. So set X label. On the X-axis we see the C, or we call them alpha values, which is 1. So C is 1 divided by alpha values. And on the y-axis, we see the accuracy. Then we plot this, and I'm getting an error. Okay, which says here, of course, when I use the training data, I can't use the validation for evaluating it, because they are of different sizes, so I have to use y-train, of course. Then let's execute this. Okay, and this will now take a little bit longer, because we now do this for loop. We have to train 50 different models with 50 different C values. And so they reach from -4 to +4, which gives us the strengths of our validation. And what we have to do here is we also have to set here the scale, the X scale we have to set to log, because we used here a log space instead of a lin space, and then the plot looks a little bit nicer. So let's wait a little bit longer. So we compute now these 50 different models for different C values, where small C values have a strong effect on regularization effect, and large C values have a mediate or a small effect. And now you can see the following plot here. So you can see here different C values, and here the accuracy. You see, and we have to also add the legend, and I also add a grid, that it's a little bit easier to see. So let's execute this again. It takes a few seconds. And now we see the following plot. So here we can see all the different C values from 10 to the -4 to 10 to the 4. So that's in log space, all the 50 different values. And in blue, we see the training accuracy. And in orange, we see the validation accuracy. And we see here, when we have no regularization, we have a model that performs very well on the training data. So, and with here, so with 10 to the -4 C values, we have here very bad accuracy. So the model increases here with the complexity, very complex model, very uncomplex model. And then we see that on the validation accuracy, it first goes up and then it decreases again. So the more complex the model gets, the better it gets on the training data, the worse it gets on the validation data. And this is something that we have to avoid. So when we select our model to reach perfect performance on our training data, we will have a very worse performance on our validation data. So what we would like to select now is the C value that leads here to the best performing model on the validation data. And this is then this line here. So it has not the best performance on the training data. It makes some error on the training data, but this way it generalizes very well to the validation data. However, in this case now, we more or less optimized our model on the validation data, and we don't know if it really generalizes to unseen data. And we will look now at the way how we can use cross-validation on the training data to find the optimal model, and then we validate it on the validation data. So therefore we can use the following package from sklearn, linear model import logistic regression CV. Logistic regression CV is a model that has already an internal cross-validation. So when we go here to the documentation, you can see there's logistic regression and there's logistic regression CV, which has an internal cross-validation if we look at it. So we can set here CS is equals to 10, which says it should try out internally on the data which we pass to it in a cross-validation mode, so CV, we can set 10 different values. And we can do here a cross-validation. So, which says the default cross-validation generator uses a stratified k-fold cross-validation. If an integer is provided, then it is the number of folds used. So the default value is 3, or it will change to 5, but we can also change here the default. Let's say that we would like to do a cross-validation with 10 folds. Then we provide here a list of different C values, and we say here which penalty it should be using and which optimizer again, or solver. So we can use this, and then we can do this internal cross-validation search automatically. So I say model 2 is then the logistic regression, but now we take CV. We would like to try out 10 different values for C. We would like to use the L2 penalty. We would like to use the LBFGS solver. We set max iter to 4000, so we use again more iterations to get more numerical stable results. And then we say we would like to do a 5-fold cross-validation. And then we fit the model, model.fit. That's the training now of the model on the training data, and the Y train. So this, when we execute this, then it's executing this model here with an internal cross-validation to find the optimal CS parameter. So scikit-learn gives us here a lot of opportunities to speed up the developmental process. And then we can say our predictions now of model to predict X-val on the validation data, and then we can copy here the stuff from above to compute the metrics, and I rename this in 2 that I don't override the variables from before, and then I copy this again. Then I first print here on the validation data 2. If I execute this, then it's doing all the computations in the backend. And then you see, okay, now we also could print here, of course, the optimal C value of the model. So print best C plus str, so model to dot C underscore. So that's the best C that is selected, which is 0.046. That led to the following model with an accuracy of 0.7, 0.68, a precision of 75%, a recall of 52%, and a message correlation of 0.39. And if you look back here at the results from above, then you see that the model improved a lot. So the accuracy improved by 9%, so from 61 to 70. The message correlation coefficient also improved. So we can see now that using regularization improves the abilities of our model in doing predictions. And we also can look again here at the model coefficients. So we look at model 2 coefficients, and then you see that the weights or the coefficients beta have not weights of 300 and minus 300 or 600 anymore. They are now shrunk down to very small values, and then this helped us then to achieve this better performance by shrinking this beta coefficient. So we can see that regularization helps us to get models that do better predictions and that reduce the complexity, and that with logistic regression CV we can do this internal cross-validation. And the last thing I would like to show you in this hands-on is how we can now do or plot ROC curves to compare these two models we now fitted in one plot. So to plot the ROC curves, as said, we have to generate a ranking of all the possible thresholds, and therefore we need some scores. And the scores we get from the decision function of our model. So the scores from our model, so model this was our logistic regression model, and model 2 was our logistic regression model with the L2 regularizer. We get first the decision function, of our xval, and then we compute FPR and TPR and the thresholds of matrix dot ROC AUC, ROC curve, and then we pass here the true label, true y-val, and the scores. And these are now the for logistic regression without regularization. And now we compute the same LR with L2 regularization. And then we change the model to model 2. And then we can plot the figure. So again, we can copy here from the figure from above the first, just all of the stuff, and then we adjust it. So what we would like to plot now is not the training and the accuracy here, so we remove this. So the X label is now the false positive rate. The Y label is the true positive rate. We remove the log scale here, but we set a limit, so X set Y lim, so Y should be between 0 and 1, and the X-axis should have the same limit from 0 to 1. And then let's plot x.plot FPR, false positive rate of model 1, TPR, we set the alpha value of 0.7 to add some transparency to the model, then we add a label, and here we say that's logistic regression, and that's the ROC AUC is equals to %2f, and then we pass here %AUC. And the same, we copy just this, we do for FPR. So we have to rename this FPR2. That's then FPR2. Then the false positive rate of our model 2, which was with regularization, the AUC2. And then we add one more plot, axis.plot, and then we say the x coordinate should be 0 and 1, and the y coordinate should be 0 and 1, and the color should be gray. The line style should be dashed, and the label should be random classifier. Then let's execute this, and then we will get the ROC plot for these two curves. So you can see here now the false positive rate, the true positive rate. Then we see here the dashed line, which is the performance of a random classifier. And then we see that both models perform better than just drawing a dice or than a random classifier. And we see that the normal logistic regression, we have to adjust this with L2 loss, that it's clear. So the blue one is the normal logistic regression. It has an AUC, an area under the curve of 60%. And when we add the regularization, then the AUC is 68%. So it's a little bit better than the blue one. And then we can compare these two classifiers on the validation data, and we see that the orange one works better on the validation data. In the homework, you will now add to this example additional regularizers like the L1 loss and the elastic net, and then you will compare all the different models. And in the end, in the homework, you will then retrain the best model on all the data and fit it and try it out on the test data, which we separated here in the beginning, but we have never used it so far. Then we can really find out how well the best model performs on unknown data. That brings me to the end of this hands-on tutorial, and see you then for the next session.